So this point is asking to evaluate the function f, and here's the function f at a not very rounded point, 1.9, 0.15, and 0.95 using linear approximation. So first thing first, I have to find a rounded point. In this case, it would be 2, 0, and 1. Then I need a gradient vector. So let's find f sub x at any point, which is going to be in here, sine of y, f sub y at any point, which is going to be x cosine of y, then f sub v z at any point, which is 1 over z, and then the next thing that we want to do is to go f sub x. We want to evaluate f sub x and f sub y and f sub z at the point 2 and 0 and 1, which this is going to be the gradient of f at 2 and 0 and 1. Evaluating f sub x at that point gives me 0. Evaluating f sub y at that point gives me 2 times 1. Evaluating f sub z gives me 1. And then from there, I write the linear approximation. So the point is 2, 0, 1. Linear approximation at that point of the f for any value is going to be the gradient times x minus 2, y minus 0, and z minus 1. So here the points goes in here because you're finding a plane, linear approximation is a plane in here, and that gradient goes here. So gradient of the f at the point. Here is the point. And then you add f at 0, 2, and 1. So f at 2 and 0 and 1 is, if I plug in x equal to 0, I made an error at the point 2, 0, and 1. So if I find that the point, I can't plug in gradient into the f at this point. So here I have to do 2 times sine of 0. So let's compute 2. It would be 2 sine of 0, which is 0, plus natural log of 1, which entire thing is 0. And so now this is going to be 0, and the linear approximation is going to be 0 times x minus 2, 2 times y, plus z minus 1. And now use this L and plug in the values that you have. So for x, you plug in 1.9. We don't have an x, so it doesn't matter. So I'm finding L to 0 and 1 of 1.9, 0.15, and 0.95. And that's 2 times plug in 0.15, and then plus z minus 1 is going to be negative 0.05. And so I have 0.3 minus 0.05 is equal to 0.25. And so function at 1.9, 0.15, and 0.95 is approximately that, basically. Again, find the gradient at the nice point, find the value of the function at the nice point, the gradient vector times the difference between nice point, between the not a rounded point and a nice point, that vector plus the value of the function gives you the value at approximation of the value at a not very nice point. I call this one the nice point, the anchor point. And here you can see the differences. That's a gradient vector plus the value of the function at the nice point. That dot gives you the entire thing.